All right, guys, thanks for coming. I was getting nervous. They didn't open the doors, and I literally thought it was going to be me and the AV guy. So I was excited when I saw everyone filing in. Okay, so probably the last thing you want on the final talk, although, yes, I guess there's an argument that if you're here for the final talk on the last day and haven't gone drinking yet or whatever, that you actually want content, right? You're here for content. So I have 4 hours of content and 110 slides. And on top of that, I have a little surprise for all y'all. Let me get that going. If you guys have your computer or your phone out, everyone here gets a GPU. So I have a URL that I'm going to give you here. So go to, I'm having a little bit of PowerPoint problems here. It's really tiny. Go to that URL. That's allocator.demo.pipeline.io/allocate. And log in. There's a bunch of examples. This is actually based on, every month or so I do like a workshop to kind of show people some of the research that I've been sharing. And this is one of the ways to express it. Also, I work for this company, Pipeline.io, that I started last July, actually 1 year and a couple weeks. We're focused on model deployment. There's a few players in the space, so we're excited. We have a Netflix background, a lot of us, so we're kind of bringing that same high scale, high availability from like Netflix into data science. And if we can, the goal is to sort of give data scientists full power from the notebook to actually deploy on their own. I say that and people kind of, especially managers tend to cringe. I saw this firsthand when I was at Netflix, and it, sort of giving people freedom and like responsibility was the big thing there, and it really changed culture and sped up a lot of things and made the data science group a lot more agile. So yeah, just trying to make this happen. Can you guys get into this instance? I'm tearing these down as fast as you guys walk out. These instances are done because they're GPUs and they're kind of expensive. Okay, so when you hit that URL, take the IP address and stick it in. Is it doing that? Is it working? Only hit just, there might be a thundering herd. I just have a tiny little Flask service that's, and this is, yeah, see, this resolution on this whole thing is jacked. It's not just PowerPoint. So I'm going to do one. I think I spun up a couple hundred just in case. Let me, so this, you would take this IP and just put it right in and it should. Okay, people can get in. Okay, so I started them about 30 minutes ago, and it takes about 31 minutes to start, so sometimes, yeah, okay. So this is what I use for the workshop. There's CUDA code in here. There's obviously TensorFlow, HDFS, Spark, so we've got, we're doing ETL with Spark, and then putting it into HDFS and pulling it out from TensorFlow. So I'm going to talk about all this stuff sort of in bits and pieces here, kind of the what I feel are sort of the most significant findings and things to share. So let me actually back up here. Tell you guys real quick who I am. I've got my own emoji, apparently. Someone made that for me. It's kind of funny. Looks just like me. They put the little Cubs hat on there. And yeah, so I run this meetup in town. We just did one Monday night here. That was pretty good. We had like a lot of GPU talk and had a reinforcement learning talk as well too. I think the next few sessions will probably be back up in San Francisco where I live, because I don't know why specifically, because it's close to my house, I guess. But yes, I like coming down here because I come down here from San Francisco and I remember why I moved to California, right? Like the weather and when I'm in San Francisco, I feel like I'm in the Antarctic or something, right? Back in Chicago. So I used to work at Databricks, used to work at Netflix. That's where my Spark background comes from, and we have a presence here, Chicago, Washington, DC, and London. But yeah, check out this meetup, and all the archives are there from the past. I think I've had this now for 2 years, right when I left Databricks. So you guys, I assume, are software engineers, data scientists. You probably have some sort of working knowledge of TensorFlow, but if not, that's okay. The talk is geared more towards like computer science type stuff as opposed to specifically TensorFlow. One thing that's interesting about this talk is that, well, yeah, really, A, that we're going to do 4 hours of like material in 45 minutes. But B, I tend to also focus on deployment and the actual scoring and the like prediction side of things. Of course, that's what Pipeline IO does. So half of it is training, because of course you have to train your model before you can deploy it. And in doing that, I discovered a lot of optimizations that like TensorFlow offers. And so the first half is kind of training optimizations, things you do at like training time to make your like model train faster, converge faster, things like that. And then there's the second half, which is things that you can do to the runtime, right? Like with TensorFlow, you can turn on like request batching. You can take the trained model and you can simplify it and sort of strip out nodes that aren't needed based on the particular input and output that you're looking for. So, right, like these are all sort of hidden gems within TensorFlow that like not a lot of people know about. To get this functionality, you have to build from source. Which I have a build from about 12 hours ago, and it took about 9 hours to build because we're building for like GPUs, and we're building all of the source in the entire code base. So not just building the pip so that you can install the pip and do a couple demos. This is for the optimization stuff as well too. So if you're wondering, the username is just root. Yeah, so just do anything to get in there. If you want to start, Bitcoin mining because you have the GPU, yeah, that's cool. Someone did it the other day. They hopped onto one of my dev servers, and I could see them poking around to see if NVIDIA drivers were installed, and then they pulled down, I think it's mine client, right? Like they did pip install mine client and passed in some, credential or whatever, and they were mining on my dev box. Yeah, so this is the GitHub repo that, like, literally the demos I'm going to show you guys are exactly the same Docker image that you guys have, and it's the same Docker image that is sitting at this repo right now. So this includes building it from scratch, turning on all the optimizations, that kind of stuff. So, right, like one thing, since like we don't have a lot of time, is I want to at least leave you guys with places you can go poke around later. And we also have a community edition, which I don't talk about here. Let me just, I guess, show it real quick if you guys want to hop on here. There's this community.pipeline.io, and you click train and deploy, and you get so you can actually do Spark models. I was just tearing up the TensorFlow one right before this, and it's a bit busted right now, but you can just deploy sort of ad hoc Python. We've got Java support. Basically, we support pretty much all the major models. It's just they're not in a state that I want to promote them in this community edition, because people were seeing errors and they were kind of getting turned off. But yeah, we have XGBoost support, scikit-learn, of course, PMML. I get a lot of requests for just simple key value things, right? I mean, the first cool use case, especially thinking about Netflix and things like that and like recommendations, is to sort of offline generate recommendations and then deploy them somewhere. And so at first we were kind of rejecting this and saying just use a database, right? But right, the goal to get data scientists to train and then push out to production kind of breaks down if like we don't give them some way to. So our solution so far has been Redis, which if you have a whole ton of data like Netflix, this costs a lot of money. Right now, Netflix is in this phase where they're for the sort of hot users, right? Like they're loaded into cache, and then people that like haven't logged in a while, their recommendations are stored. I think in RocksDB is what they were going with, and as people log in, it'll pull it from disk and then load it in, and yeah. So you can check that out. You can play around with it. any links that I share from now on will be referenced. I just stood this up about a week or so ago. So let me get back to. All right, so if you get in with the username root, no password, you can kind of poke around and follow some of the things. I'm just going to speed through. So there again is the URL. If you came in late, if you go to that top URL, grab yourself an IP. It's a GPU, and there's just use the username root. This link will not work after you guys leave also, because I sometimes leave it up. Yeah, my slides got a little munged. We're playing with the resolution and stuff, and my slides got munged here. But yeah, so on here we have TensorBoard and HDFS, like I said, and Spark. So the first thing, yes, I want to talk about GPUs for a sec. I think, right, there's a lot of people, including myself, that are kind of like mystified by these things, right? Like, where do they come from? Or like, we know what they were, right? Like, we know where they came from, but why are they relevant? What's going on? So as of the Pascal P100, which came out at the GPU Tech Conference, which was here, I think, last year, the Pascal P100 came out, and it offered this concept of half precision. So normal GPU cores, which there's 4,000, 5,000 of these things, can handle the full floating point 32 precision. So that's kind of normal precision. And with this newer P100 like hardware, and of course from really here on out, so this new one is called the Volta V100, came out just maybe 2 months ago at the most recent GPU Tech Conference. Yeah, so these can handle this concept of this half precision. And so if you can sort of get your floating point 32 down into floating point 16, and that's good enough, right? This is all kind of hand-wavy, deep, right, like deep learning stuff anyway. So you can actually double your throughput, because now you can fit, right, like 2 of these FP16s onto one single FP32 core, and they're, right, like vectorized in parallel. So yeah, half precision's kind of the new, right, like full precision. And this is actually pretty good. So yeah, there's the speed up there, 21 teraflops. The GPU instances that I've given you and that I have access and that are not these P100s. They're actually the K80s. That just the cloud providers haven't started to release those yet. I think Google is pretty soon going to have the P100s, and same with Amazon. Google also has this thing, the TPU, and I'm going to talk about this in the context of the new Volta V100. The TPU by Google stands for Tensor Processing Unit, and this is optimized for the forward propagation, for the scoring side of things, for the prediction side of things. And so the NVIDIA folks, not to be left out, said, yeah, you guys really have these TPUs, but we'll sort of one-up you and give you the existing GPU cores, which are good for the back propagation and for the training, and we'll now tack on 672 of these tensor cores. So it's essentially TPUs. The workload, would shift to the TPU for the forward prop and then for the training. So it's sort of a multi-purpose thing, right? Versus Google, which is just the TPU side of things. A couple other improvements there for the new V100, but yeah, that's the big one. And with the V100 also, you can do mixed floating point and mixed half precision and normal precision, whereas before you had to choose one or the other. I'm going to skip over some of the CUDA stuff, but the big thing here with CUDA 9 is you have sort of fine-grained synchronization, right, like semantics now. So, right, like thread synchronization semantics. So, I'm sure, right, like we all live here in the Bay Area, I'm sure that we all have a copy of Java concurrency in practice, right? It's kind of the standard when you were like learning about Java's memory model and threading and atomics and all that stuff. When you would go to do CUDA programming, it was completely barbaric, and you had to sort of unlearn all that stuff, because like you didn't have ways to yield. It was meant for single instruction, multiple thread, right? Just plow through. No sort of if statements, no branches. If you start to branch, you leave cores like idle. So yeah, if statements in CUDA, if you're doing code reviews, these things stand out as being bad. But with CUDA 9 now, so there's the explicit synchronization, there's ways to yield, and to like sort of interleave stuff. So there's some tooling for CUDA stuff. I'm going to skip through that. This is a key concept. CUDA streams, which came out in about, I think CUDA 5 or 6. So this is definitely not new, but this is heavily used by TensorFlow. So CUDA streams, yes, I should probably describe the problem before CUDA streams, which was the GPU could only do one thing at like the same time. So it could either be pulling data in from the CPU RAM, which is an expensive process, or it could be computing. And now there's ways to sort of interleave that. So at the same time data is coming down, the GPU can actually continue to process. So when it's done with the current batch, it can then pull it that like data has been transferred down and it's ready to. So before the GPU was constantly sort of thrashing and just sitting idle, and the goal here is to keep these GPUs saturated. And yeah, so CUDA streams allows this. This is very important. And I'm going to talk about the Q framework here in a bit. This is super important. There's actually even newer API that will drop with TensorFlow 1.2. It's out right now. Actually, like you guys have yesterday's master build from TensorFlow 1.2. It's called Dataset. And if you guys come from a Spark background, like I certainly do with Databricks. I was at Databricks when we migrated people from the RDDs to DataFrame, and then again from DataFrame to Dataset. So I get like a little twitchy when I hear about the Dataset API, but because I feel like it's going to change. If you guys want to run through some of the notebooks, I'm going to skip the notebooks. I have images of sort of the sort of highlights here. I said this isn't kind of an intro level class on TensorFlow, talk on TensorFlow, but I do want to highlight some of the key terms here. So two things to there's probably 4 or 5 things to take away based on this slide overall, but you have a graph, and so similar to Spark, you're kind of building up this directed acyclic graph. Here, it's more mathematical, numerical type of operation, so it's not your joins and filters, maps, and that kind of thing. It's more take these 2 matrices, multiply them. This is linear regression, and you're trying to learn what's in sort of light or blue or whatever it is, that lower left. You're learning those variables, right? Like they're often called weights or like parameters, just sort of legacy terms. In TensorFlow's API, you'll see the term variable. So that's what you're learning, right? You're trying to learn like W and B, right? It's just your simple y equals mx plus b kind of thing, y equals w, x plus b. X is what you're feeding in. So that lower right, I kind of have the sort of actor highlighted with those 2 hyphens around it. So the user feeds in input. At training time, it's feeding in both the input and the label or the answer key, right? So it's feeding in both x and y or whatever, right? So you feed data in. So that's an important concept, and you fetch data out. And fetching comes from typically a TensorFlow operation. So there's no variable, there's no thing that's actually giving you this result. You fetch it from an operation, which was a little bit weird for me to grok when I was first studying TensorFlow, but that's an important concept because you'll hear and see people talk about feeds and fetches all the time. And you just want to kind of substitute input and output and that kind of thing. There's cases where there could be multiple outputs, and this is multi-headed inference is the kind of fancy term for it. And this is a case where you want the model to give you the score, that prediction, and give you maybe that last layer for your neural network. And that can then get fed into another model. So you're using that same one model with the same single set of those inputs to give you the prediction and to feature engineer to get piped into the next model. And then that would also produce a classification, and you can compare and average or whatever you want to do. So keep that in mind. And tensors are flowing, that's where the term comes from. And then, these operations are typically mathematical ones, but it's generic enough within TensorFlow where things like writing out checkpoints and summaries of your scalars that you're training, those variables that you're training, you can write them out after 100 steps or something like that. And so those actions are also called operations. So real quick, also devices. This is kind of important. Just know that you can like manually assign CPU or GPU. You can also assign, this hasn't yet been turned on by default, but at some point this will be. This is the XLA stuff. I'm sort of jumping ahead a little bit, but it stands for Accelerated Linear Algebra. You can kind of hint to like TensorFlow to yes, use the CPU for this particular operation or the GPU, but also try to just-in-time compile. And so these are some of these like training time optimizations that you can control. So by default, again, this will be turned on. Right now, it's this whole feature is experimental. The Accelerated Linear Algebra framework is experimental. And think of it like a compiler IR, right? Like an intermediate representation, similar to like LLVM. And what's interesting is that the XLA framework uses like LLVM at the very, very bottom. So as long as they can take your sort of logical graph, right? This is TensorFlow, can take that sort of logical graph and get it into LLVM, then you could go from like LLVM down to the specific hardware for the ARM or for the x86 or for the NVIDIA PTX, right? That's the equivalent of, that's their like hardware instruction set. So we'll talk a little bit about that. Tensor board. There's always, I can kind of name a few reasons why I think Spark, for example, took off. Just real quick, things like Spark ML was always packaged with Spark kind of from the beginning, and Graph, and people are always really intrigued by like machine learning, and so it was different than when you were presented like MapReduce and then shown like Mahout maybe 6 or like a year later or something like that. It was all kind of right there. So, and this in like my opinion is one reason why TensorFlow has picked up a lot of steam is you can actually get sort of insight like during training time. So this is what I was saying when you're writing out those variables that you're learning, or in this case this is the actual loss. So this is the difference between what I guessed would be y and then the actual y during training time, and you can what you want to do, of course, is get to 0, right? So having some sort of insight, it's still not telling you what the network's learning, and it's still difficult to grok from a human standpoint what's going on here. I mean, this is really easy, it's just linear regression, but this gives you a little bit more insight. Right now, you have to kind of give it some like boilerplate code. There's sort of higher level APIs like Keras and things like that that will do this for you. This is important too. This is like primarily Hadoop, like big data processing type of conference. So I want to highlight this. This is how you would integrate Spark into TensorFlow into your existing pipelines. There's this ecosystem project within at like TensorFlow, and this is the Maven coordinates, and you can pull this into your Spark app, for example, your Spark job, and you can actually generate TF records, which is the native, it's kind of like sequence file, for MapReduce. So you can, if you want to create those TF records, it's not mandatory, but because TensorFlow can understand CSVs and things like that. But when you're really trying to like optimize this pipeline, like this is something that you definitely would want to check out. And then from here, then like TensorFlow would like pick it up from HDFS or from S3 and then do its training after Spark has done sort of the batch heavy lifting. I think I'm going to skip this, but the big thing here is use these queues. So queues, let me just show you a picture. This is, yes, I mentioned CUDA and streams, and the goal here is to train as many samples or batches of data as possible. Just get huge throughput through, and there's quite a bit of bottlenecks, as you can imagine. These pipelines can be pretty complex. Take like image processing, for example. If you're trying to train some sort of image classifier, you would first have to pull these images, from HDFS or from S3, wherever, crop them, right? Like resize them, maybe like grayscale them, things like that to sort of normalize the data, just like you would with any machine learning pipeline. And also too, because we're using stochastic mini batch gradient descent. So stochastic, we want randomness, right? So as that data is coming in, like if there was some order that these files were placed on disk, some sort of time series order that isn't meant to be preserved or learned by the network, you want to then shuffle, right? Because you don't want the network learning this sort of implicit ordering. So you want to shuffle. And then, so these queues, this is more than just like a computer science queue, right? That we think of. This is actual code. These are pipelines that you're building. So you would have a shuffler, cropping, shuffling, all that kind of stuff. You can pull from Kafka. This can solve the small files problem also. So when you're back here, this is like the classic HDFS small files problem where you want to sort of, when you're creating these TF records or just sort of munging this data back into CSVs or back into JSON, you would want to batch these up into larger batches, which then would improve some of the throughput here through these queues. Things to keep in mind, batch size on these queues. So let's say, these GPUs typically have about 12 gigs of RAM, and if you take a look at the average size of your JPEGs, you would divide that into 12 gigs, and yes, maybe that's 64, like JPEGs. That's all you can feed in based on memory. And so this is after it's been cropped and grayscaled and all that kind of stuff. So just keep a close eye on the batch size. Here's some tooling. This is actually getting a little bit easier. This kind of stuff is getting rolled into TensorBoard, but the point here is that you can actually see where time is being spent, and you can't really see it, but those, I think the second, third, fourth, fifth lines there are the GPU streams. So it shows you the entire device, but then also breaks it down by stream. So you can kind of keep an eye on where time is being spent. And again, this does require some sort of boilerplate that you have to stick into your code to generate this, which is then read by the Google Web Tracing Framework, which is some magical framework to do these, to render these timelines. So you can take a look if you want to look at feeding a queue from HDFS. The other thing, it's got munged, is keep in mind too that when people talk to you about TensorFlow model, sometimes you want to probe and say which part of the model are you talking about? If you never use the term model again and just talk about graph, you're graph def and your variables. People know what you're talking about. If you say model, that starts to get confusing. Because really, the concept of a model kind of depends on if you're if you plan to continue training, in which case you keep your graph and your variable separate, because that graph is static, right? But these variables continue to get trained and to get updated, and you would checkpoint them every hour or every 500 steps or 1,000 steps. And at some point, when you kind of run out of data, it's sort of frozen. And then when you go to deploy, that's when the context of the term model changes, and now you're actually burning in those variables into the model itself as constants, and then it's just a forward prop, right? Yes, how much time do we have? 10? 10 minutes. Oh man, we have, all right, 60 more slides. So yeah, just keep in mind graph def is static, variables change. And this, some of you might be thinking, wow, this sounds a lot like this, like partial fit, within scikit-learn. Instead of calling fit on, like a big chunk of data, you would call partial fit, and you can sort of online train, Like a lot of people don't know that about scikit-learn, but they're actually, unlike a lot of those linear models, there's this method, partial fit, where it's sort of going to, keep things open to change. But when you do go to like deploy, that's when you have to actually freeze. There's a debugger. It's kind of funny. It's a punch card picture. Yeah, that's always a big hit here in the Bay Area. If you've never heard of batch normalization, this paper came out in 2015. This is definitely something to use. I haven't talked to a single person who claims that this has slowed down their training or negatively impacted. The final model is probably just as accurate, sometimes more accurate. speeds up training. There's pretty much nothing bad about batch normalization. And just from a intuition standpoint, what's happening here is, yes, I mentioned the stochasticness of data being really pulled in. It's being shuffled, it's being randomized. So picture linear like regression here, and picture that training data is coming in, and if you plot that batch, that single mini batch, right, like that distribution could be all over the place, right? And so the network is naturally, so A, it's trying to learn these weights, but then B, it's also trying to adjust for this like wildly changing distribution just based on the randomness of how those batches were chosen. So batch normalization attempts to sort of normalize that. If I think this is an implementation of sort of a moving average of the mean and variance. And once you've gone through all of the data and you're finished training, there's sort of this final mean and final variance that you can burn into the model right before you go to serve it. And then, yeah. So right, check that out. It's pretty cool stuff. Real quick, actually kind of, yeah. So I'm going to talk about multi-GPU training on a single node. And then the next slide is distributed training across multiple nodes, but it's essentially the same concept. This is a little bit easier to grok. CPU, picture that as your Spark master or your Spark driver. And it's maintaining the current value of these variables that you're training. And this is good because CPUs have huge memory space, right, that they can access. They're not bound by right, like something like GPU, where it's only 12 gig. They can go up, terabytes and terabytes. So CPUs are good at storing. The only thing that you're doing here is just a simple average, and yeah, so I'll talk about this here in a sec. But so picture each GPU has that model loaded in it, right? And think of it just like Spark. When you have a whole ton of Spark workers, each worker has that same snippet of code, the same Python, the same Scala, whatever. So similarly, each of these GPUs has one model, has that same model stored in memory. And it's just getting different batches of data. So after one pass through, for example, each of these GPUs will have seen 50% of the data. You would typically then want to go back and do another epoch or epoch or something like that, which is one more full pass through the data. That way, these GPUs are exposed to different sort of subsets of the data, so it's not always 50-50. And each GPU then, when it's figuring out that loss and sees that you guessed, and now, right, like W should, so that first GPU might say W should go up by 10, and the second GPU, based on its subset of data, it's like mini batch, says, I think W should go down by 5, and then that CPU gets both like recommendations for all of the variables that you're training, right? So there could be tons. For us, it's just W and B. And for each variable, it's going to average, and then that's the final value, right? Or that's the final delta. That's the gradient, right? That's it. Okay. So the CPU sort of acts like this controller, and similar kind of concept here, distributed land. That first one is what we were just talking about, which is one CPU and two GPUs. The second one is, so it's the same graph from you as the data scientist building up this graph. You don't have to think about this distribution, right? Yeah, so TensorFlow will put in send and receive, and it's all gRPC, and it's all, protobuf and all the fancy stuff like beneath the covers. And then the parameter server, that's highlighted. That's basically now the CPU, or it's playing the same role that the CPU was in the single node back here. So the parameter server does the averaging, except instead of on a single node, it's now across many nodes. And each GPU on each node, so if there's 4 per node, each GPU has its hint or its gradient, right? Like which way should each of these variables go? And each GPU, each worker will do a pre-aggregation, pre-average. This is kind of a slight optimization, but I'll share it with you guys because Spark actually does a lot of this as well. To minimize communication between each worker and the parameter server, so that the parameter server now has to deal with just three numbers that have been pre-averaged versus 3 times the number of GPUs, 12. So, and the parameter server then does an average and then broadcasts out. Some of you might say, oh wow, this is all great, but there's times when maybe one of these workers is slow, or the network is slow between worker 3 and the parameter server. Wasn't really a big deal here because this is on the same board and all that, and you have more control over this. But once you start to introduce in this multi-node, and there's actually multiple workers, and now there's this network involved now, things could get a little bit sour. So what you'd want to do potentially is switch to an asynchronous sort of update mode, where that parameter server will wait for a little bit of time. If it doesn't get it, it's just going to average whatever it's whoever has reported back during that step, and it's then going to broadcast out. So there's a slight possibility here that you might not converge because some of these nodes might be getting stale values, or their hints aren't being incorporated. But in a truly distributed fashion, and in fact in a lot of the benchmarks and things like that coming out of Google, they definitely use the asynchronous. Yes, keep in mind too that TensorFlow was designed to be distributed, right? So this is actually something that isn't talked about a lot. When Google builds anything, it's not for single node. It's not, it's definitely has to have distribution. It was a little bit confusing because when TensorFlow first came out, they hadn't yet open sourced gRPC, or there was still some kind of back and forth with the actual way that they're doing that distribution. But they still want to get TensorFlow out. And so people started to compare TensorFlow to Caffe and to Theano, and because TensorFlow is optimized for the distribution case where has to go across workers, some of these other frameworks were starting to dominate. And I think, in fact, at the Spark Summit, I think it was last week, 2 weeks ago, they mentioned that so Databricks is spending time on sort of optimizing Spark for the single node case. And there's 2 reasons for this. There's people doing benchmarks and just sort of doing it on their laptop, similar to how they do scikit-learn or R. And they made a choice early on that even the local mode Spark would still go through all the serialization and deserialization and all that. And that's so that they can catch any bugs, right? Because Spark was also designed to be fully distributed. And so some of the hints, that they're saying lead us to believe that they'll sort of have separate code paths now for all local, right, which will just be in memory. And the second reason for this is these, there's these X1 instances now that are commodity instances that we can get from Amazon that have 2 terabytes of RAM. This is starting to, to become feasible that you have one single worker, one Spark worker, and you just give it all the RAM you can. And it reduces all the sort of overhead. Data parallel versus model parallel. Quick summary here, Spark is data parallel, so how you and MapReduce, this is all data parallel. It's the same code, the same model that's seeing just small partitions of the data. If there's a case where your model, so not just your graph, right? Your graph is actually pretty thin. Think of it like a logical plan. If that model physically so if that model and the sort of temporary variables that have to be maintained when it's calculating the gradients and doing the partial derivatives, if that whole calculation can't fit into GPU RAM, which is 12 gig, which is a lot, that's when you have to cut the model and actually split the graph over multiple nodes. And there's not a lot of people that do this. Yes, obviously Google, Facebook, these kind of guys have to distribute, but that's where things start to get really tricky because you really have to understand the graph. If you're making changes to the graph, you could screw this up. You want to sort of co-locate nodes that are talking to each other, and just trying to figure out which sort of edges to cut on or even nodes to distribute gets really tricky. It's the classic problem with GraphX, if you've ever done any Spark GraphX or any Neo4j distribution. All right, distributed TensorFlow. I think I kind of beat this here. There's this concept of a chief, one of the workers. If the chief goes down, that's a really bad day. Chief is responsible for things like checkpoints and right, like telling these parameter servers now's a good time to save out to HDFS. On that same note, there's this pattern I've been seeing more and more of recently where I'm sure right, like most of us are familiar with if you get a big batch of training data, right? You have, someone gives you training data, you split it up 80% for training, 20% for your model validation, that the model, when it's being trained, doesn't see at all that 20, or shouldn't see at all that 20%. And when you have these sort of long-running training jobs, you don't want to burden the training step with the validation step. So training it's like way more complicated, right? There's like way more like computations going on during training than just simply comparing, just doing like a root mean squared error kind of thing just to validate. So think of this as separate clusters. There's this training cluster, and this is kind of split along 80%, 20%. So that training cluster, its full-time job is to just train and figure out gradients and store weights. Every hour, let's say, it's going to write it out it's going to tell parameter server to dump it to S3 or to HDFS. And then at that time, there's this validation cluster that spins up and grabs that like most recent like checkpoint. And then if things start to get a little wonky, if your validation starts to look bad, that means that you're starting to overfit. And so you'd want to back off on the training or change the model or change the graph, which is one of your hyperparameters, right? Like you can think of the graph as a hyperparameter. All right, I'm getting swirled. Here's XLA stuff. Yes, all of these slides are out there, by the way. If you go to pipeline.io in the bottom right, there's like links to SlideShare, and there's a bunch of videos and stuff. So here's there's like LLVM as the final step there. Think of this just like your logical plan, and then it gets compiled into it gets optimized, and constant folding and filters before joins and things like that, and then gets physically compiled down from LLVM. Here's the just-in-time compiler in action. So this is using the XLA stuff. So like before things were being just-in-time compiled, they were separate operations. And if you have separate operations, you're constantly pulling data in from memory, right, like hopefully L1 cache, right, like L2 cache. But you're constantly loading stuff and then right, like putting it back into cache. If you can convert all of those into one function, so this is what Spark does, for example, with Project Tungsten, especially the second part of Project Tungsten, which hit in Spark 2.0, where it's physically fusing together. It's like it sees what you're trying to do from your like logical plan, and it is physically going to generate one Java function. It first right, like builds out the big source string. It's like literally a string, and then gets compiled into bytecode on the fly, cached, of course, so that the next time it sees this, it'll know what it is. So there's huge gains when you can sort of fuse together operators. Here's a visualization of this. You guys can play with it if you'd like. GPU version. This is cool, the AOT compiler. So this also uses XLA, except this is after you've trained. So from this point on is the inference stuff. In fact, I think I even have, we're done with training. We're not going to talk about training anymore. We're going to talk about the inference. So this is a pretty cool tool. The goal here is to create a binary that you can link into your app that has the bare minimum. So from your feed to the fetch, what you do is right, like call this TF compile thing. You pass it to your graph. You then tell it your feeds and your fetches, which the from and the to. And it's going to go through and just pull in the bare minimum needed from TensorFlow runtime, which is about 30 megs, so you don't want the whole thing, and from the operating system, right? And it's going to link all that. You have one big thing that you can then, or one really relatively small thing that you can then link in to your app. And I've seen models go from 60, 70 meg. That's the size of this sort of final binary that has to run on a tiny sensor or something like that. Down to 600K. So some pretty good improvements. Graph transform tool. This is a formal tool that kind of came out of the initial, there were like a bunch of scripts people were doing to sort of hack together and change the graph after it was trained. This is our simple linear like regression when it's done being trained by TensorFlow. And so again, this is more than just the matrix multiply and the add. Right. This is all the log summaries and all that stuff. So with a couple quick graph transforms, and again, this is on a trained model. So we're just looking at the graph. We're just stripping out nodes. Yeah, we can get it down. And it like literally reduces from, I think this model was 20K down to 400 bytes. So a couple more, you can do constant folding, batch norms, that's that batch norm folding I was talking about. Quantization's a little complex for 32 seconds, but the gist here is once you've trained, you look at all of your variables, and because you trained at, like, let's say FP32, there's this sort of unlimited, I mean, it's not truly unlimited, but there's this huge range that these floats can fall into. And if you want to store all those, you can, or you can sort of like plot these and kind of fit them into just a really much smaller 8-bit representation. And this will greatly reduce the size of your model, of course, or your that you can then deploy on these super small devices. Not phones are like relatively large. So nothing really changes with the graph, except you just now have a much smaller. And from an accuracy standpoint, things are pretty accurate. You have to kind of play to figure out where it makes sense for you. Activation quantizations, another concept. TensorFlow serving. Here's the multi-headed inference stuff here. So again, you have one set of inputs, multiple outputs. You can link TensorFlow serving into your code if you want to do some custom stuff. Here's a freezing, right? So again, these are tools that you have to build from source. You have to compile. This is where we're turning, so there's two constants there now. That's our final W and our final B have been burned into, and so they're not changing like this placeholder, which is X. That's your feed, add is your fetch. And I think there's last slide here on request batching. So you have multiple requests coming from really multiple devices throughout the world. They happen to end up on the exact same TensorFlow serving instance. You can tell TensorFlow serving to hold up, wait 50 milliseconds or 5 milliseconds, batch them into one big matrix multiply, pass it to the GPU, calculate it, and pull it back. Because you know the offsets of how this final thing, you can then split it back and send it to each client that might be across the world, each separate client. So that's it. Any questions? I don't think we have time for questions. Yeah, that's always my goal, is to talk so no one can ask questions. So, thank you.